Some of you might have heard me as one of the two people who broke the Bitcoin mining protocol. That's something that I did for fun on the side. The main thing that I do is data management. And today I want to tell you about a new system that we developed for large data infrastructure. And this is a technical talk, or it appears to be a technical talk, and I do want to get across 3 technical ideas to you today. But deep down, it's a spiritual talk. It's a talk about how something that a lot of people thought was not possible is actually completely possible and doable. And I want to sort of slowly get into this. But let's roll back and let's go back to maybe 15 years ago or so. Back then, you will remember that the infrastructure that we used to store our data and recall it was essentially relational database management systems. And these things, of course, have their benefits. But people found that these RDBMSs were difficult to scale and difficult to get to perform with low latency and high throughput. And that begat the NoSQL revolution. And we started seeing the Dynamo and Dynamo clone, or Dynamo-like systems, or Dynamo-inspired systems. So these NoSQL systems are wonderful in many ways, but they all share some common problems. And all of these common problems have their root cause at the way in which the data is partitioned across a data center. And I want to tell you a little bit about these problems. They can be grouped into 3: search-related problems, that is recall problems, consistency problems, and fault tolerance problems. So before I tell you why these problems emerge, let me tell you a little bit about sort of what makes this happen. And at their core, all of these Dynamo-like systems look kind of similar. What they do is they take a data center, a set of hosts, and they partition the data across these set of hosts using a trick invented by an MIT colleague of mine called consistent hashing. This is a very clever idea and very simple idea at its core. If I have a data item with a particular key, I hash that key, and I locate the data at a server closest to that key in some virtual space that I've created. This space is typically one-dimensional. You can think of it as a circle if you like. That's how I like to do it because it's simplest. And so in this case up here, if I have an object with key k, it ends up being located on that server. And when it's time to recall this data, I go to the server and recall it. And that's a wonderful, nice, easy thing to do. The problem, of course, comes when I try to do a search. If I store the Robert Escriva object with his key over here, rescrive is his username. If I store it under his username, and I want to recall it by his last name, Escriva, that's a bit hard to do, because in consistent hashing, I ended up destroying the locality of the data. An Escriva family member could be located on any one of these hosts, and to recall all of the Escrivas, I have to contact and talk to every single host. And that's partly why searches are so slow, and that's partly why they are so hard to get right in these systems. So the second problem has to do with consistency. It's very difficult to keep your data consistent when it's replicated across a cluster like this. This is especially so when the cluster management software does not necessarily give you a consistent view. So take, for example, the case of 2 clients, one on the left and one on the right. Now, the guy on the left, for whatever reason, thinks that these 2 servers are down, or these 5 servers are down, or however many you might imagine. Suppose you're doing n replication. If he thinks that those n guys are down, he's going to end up storing his data on the closest servers, in which case those are going to be these 2. So that's fine. Except this other fellow, this client on the right, he might disagree on which servers are up and which servers are down. So he might instead store his data on these 2 servers. And so therefore, when you ask this guy for the latest copy of a data item, he is going to query these hosts, and this guy might query those hosts. And that would, of course, yield answers that would differ from each other. And that, of course, is at the root of the consistency problems that you see in first-generation NoSQL systems. The next issue, and the final one that I'm going to focus on today, has to do with fault tolerance. In a lot of these systems, there is a great emphasis placed on performance for good reason. And we, of course, don't want to take that away. But what they do to get their performance, partly, is they take your writes as soon as possible on any host, and in the background try to sort of push those written objects to replicas. So this is a good idea. It's a good system design principle, perhaps. But what it opens is a window of opportunity for a failer to take away the only copy of the of the most recently written data item. So it's highly possible for these systems to lose data. And if you actually looked at Jepson reports for any of these first-generation NoSQL stores, you see that under conditions where the network is under churn or the system is congested, they actually lose your rights. And that is not a good situation if you want to compute anything worth of some value. So what do I want to do today? I want to tell you about HyperDex, the new NoSQL system. And I want to tell you about what makes it tick. What are the core technical contributions behind the scenes that make it give you a high-performance, consistent, available, partition-tolerant, and scalable system. Now, I mentioned a lot of words there, a lot of buzzwords, a lot of properties of a system. And three of them might actually sort of raise your ire. I mentioned consistent, available, and partition tolerant. How many people here have heard of the CAP Theorem? Okay, so there is a very famous theorem in distributed data management circles called the CAP Theorem. And it goes essentially as follows. Consistency, availability, and partition tolerance, pick at most 2. And it's kind of interesting that I'm offering you a system that actually achieves all 3 of them. So I will, at the end of my talk, go back to why the CAP theorem is still correct. I'm not saying it's wrong, but why it's not binding for us and how it's possible to build a system that actually has these 3 properties. So let me tell you a little bit about how the system is structured. And the very first idea, the one that actually makes it tick, is a new place to locate data items such that we preserve their locality. It's called hyperspace hashing. It's different from consistent hashing. And so what I'm going to do right now is give you a fairly in-depth idea of how hyperspace hashing works. I'll talk a little bit about the value-dependent chaining idea that also piggybacks on that fundamental sort of data organization scheme. And then I'll tell you a little bit about the performance of the system. So here's the core idea. If we were in the business of storing objects using consistent hashing, we would store those objects under their primary key only. And that makes it easy to recall items by primary key and fairly difficult to recall them by secondary attributes. So here's what we do instead with hyperspace hashing. When we have an object to store, let's say we're storing objects that are essentially Rolodex items. You have first name, last name, telephone numbers. What we do is we create in our mind so far, we haven't converted into a system at the moment. I'll convert it into a system in like 3 or 4 slides. So at the moment, I want you to imagine that we create a virtual space, a multidimensional space, where each of the axes corresponds to an attribute. So this is the x-axis is the first name, the y-axis is the last name, the z-axis is the phone number that I want to store. And when I have an object like Neil Armstrong and a phone number, what I do is instead of doing a consistent hashing on the primary key, I compute a position for this object in this virtual space by hashing each and every one of the attributes independently. So I take the hash of Neil, and that gives me an X number. I take the hash of Armstrong, that gives me a Y number. And I take the hash of this phone number. The hash of a phone number is probably itself, so it's just a number. And that gives me a point in space that represents this object. And I will keep this in mind, and this will help me locate the object later. Now, if I were to have another object, say for Lance Armstrong, so Lance has a different first name, but he has the same Armstrong last name, and he has a different phone number. If I have Neil Diamond, well, he has the same first name as Neil Armstrong, and has a different last name, so therefore he's at a different location up in this multi-dimensional space. So I hope that's sort of gives you an idea of how we attach to every object a coordinate in this multidimensional space. And now the next thing we do is we slice this space up. The technical term is tessellate, but it's really just slice it up into cubes and assign each cube to a server in our data center. So the Neil Armstrong object ended up on that server. The Lance Armstrong object ended up on that server, and so forth. Now, this organization of data is drastically different from consistent hashing and has some really nice properties. It has the property that if I'm looking for, let's say, everybody named Neil, I do not need to contact every single server. I need only contact those servers that intersect with this yellow plane. So which ones are those? Well, that's only half the servers in my data center. I suddenly made the search operation much more efficient. If I were to look for all the Armstrongs, I need only contact those servers that intersect this gray plane, these 4. And if I'm looking for all the Neil Armstrongs, I need not contact everybody. I need only contact those people, those servers that intersect this particular line right up here. And further, if I were to look for a Neil Armstrong in the 607 area code, that's just a tiny line segment. It's just this bit right here. And I can get that answer very efficiently simply by contacting a single server. So what we did here was a very cool, I think, and very elegant data placement trick. Instead of destroying the locality of our data, we preserved it. And that preservation allows us to recall it very quickly by contacting the minimal number of servers we need to contact. So you might say, well, that's fine and good, but I have really highly multidimensional data. I have data with hundreds of secondary attributes, and so your spaces might be really big. And you'd be right. So to handle this case, we do this thing called subspace partitioning. So instead of taking data with, let's say, d dimensions, say hundreds of dimensions, what we do is we divide it up into smaller subspaces of lower dimensionality. So for example, if we have user data, we might actually take out the primary key and use it as the index into a single dimensional space. When the first name, last name, telephone number might constitute a different subspace. Gender and age might be a different subspace. So when there is a query that says, give me all my users who are women between the ages of 30 and 40, well then I can just query in this subspace. Give me Neil Armstrongs in the 607, I can answer that using this other subspace. So one way to look at this is, if you're familiar with RDBMS, is these are kind of like materialized views, if you will, in that they allow your queries to go much faster, and they partition the data and simplify the organization of your data. So, okay, so what does this give us? This gives us one fix to one of the 3 problems I mentioned. It makes our searches efficient, and there's a critical thing to note. So some of you might say, well, I could do this with indices under MongoDB, or Cassandra has this and that. That's all true, but what I showed you is decidedly not an index. I did not tell you how to maintain or build a secondary data structure. There is no secondary data structure involved. We're not keeping a copy of an auxiliary copy of data at all. What we're doing, all we're doing, in fact, is simply coming up with a different trick for placing the data. And because I don't have to maintain an auxiliary data structure, it's going to be quite possible to consistently update my data and to give you the latest copy of the data whenever you need to. So that's going to be kind of a crucial trick, and that's what I want to talk about next. So one thing to notice is, okay, so fine, we came up with a new way of placing data. It's kind of neat, it's elegant, but it actually has some problems. So you might say, well, look, before I was just placing the data wherever the primary key pointed to. Now there are multiple copies of the data. Now it's going to be kind of difficult to, what you're going to have to do is, if the data changes, you might have to relocate it from one server to another. And doing so in a consistent manner is actually difficult, because if you delete the old copy and reinsert the new copy, there's a window of opportunity when the object has disappeared from your system. So that's a strange thing to have. So what I want to show you next is a protocol for updating copies of this data, so that whenever somebody does a query, they get the most recent version at all times. So this we call value-dependent chaining. And another name for it is the Norwegian Army Protocol. Actually, I'm not sure if Spain still has mandatory military service, but those of you, in fact, I have done this too, who have been in the Army, know that no matter how smart the people in the platoon are, as a group, a platoon is just kind of very, very, very slow on the uptake. So what you do typically is you line them up, and you have them repeat an order one by one, so that you know that every single conscript in your army has actually heard the order. So that's essentially the core idea in value-dependent chaining. So here is, let me illustrate it for you. So here is our data center with a number of servers, let's say 4 servers in this case, and here are our subspaces. So we have a key subspace, we have this A and B axes and C and D axes. So this is, I don't know what these could be, first name, last name, age, gender, that kind of thing. So suppose I want to insert an object into this with the following attributes, and I want you to pay attention to this A and B attribute. So when A is 1 and B is 1, well, the object falls in this location onto this blue server, let's say. The way we do these updates is we don't actually spray the updates and pray that they get to their destination, but instead we organize these servers into a chain, where the first guy we call the row leader, and the others are essentially holding replicas of that object for purposes of supporting a search. So in this case, we would be doing a put, and the put would go to this server, then to this server, then to this server, and it would only be acknowledged when it has been written to all of them. So if this guy says, yes, I got it, then this guy says, yes, I got it, and this guy says, okay, your write has been performed. There is no notion of a write that has been partially completed. The client is not led to believe that his write is committed unless it has been committed to all replicas. And this, I think, is a critical property for any system that holds valuable data. So the next thing you want to do, of course, is suppose somebody changes this object. They want to change this attribute A to 0 and B to 0. So that's fine, except as I mentioned, to do this properly, what you cannot do is delete it and reinsert it. What we instead do is create a chain of the following kind. A chain where the chain actually contacts the old location of the data, then goes to the new location. And so when this new write is being performed, it goes to the row leader, to the blue, to the green, and to the last fellow. When the last fellow says, OK, I'm done, the green one says, I am done too. I have committed the new version of the data. And when this guy acknowledges it, the blue one says, OK, this is time when I know that the new item has been committed to another server, and I can safely delete my own old copy. And after that point, the data has been safely moved to this server, and the system can actually forget all about its previous traces on the blue node. This is a crucial property. Our system does not have to have tombstones, as some other systems do. It does not have to have long-lived state left behind by operations. So we don't have to worry about, well, I saw an out-of-date version, et cetera, et cetera. We know exactly where the newest version is. It's over here. And this row leader is crucial in sequencing the operations, in sequencing the gets and the puts one after each other, such that when I do a get, I always see the results of the latest put. So, and if there's another update, it's great. These chains don't have to get longer and longer. All they have to do is contact the previous location. So now the nice thing about value-dependent chaining, you might say, OK, well, you came up with a new way of locating the data. You showed us this other trick, this protocol called value-dependent chaining that sort of fixes the bugs or fixes the problems that your hyperspace hashing introduced. So what, right? Well, so the nice thing about this protocol is that it easily admits fault tolerance. So if I were to create, if I wanted my data center to be able to withstand a fault, all I need to do is put some servers that are copies of each other alongside my chains. So in this case, if I were to look at the previous operation, what I would have to do to be able to withstand a fault is just have a replica for each item. And should something happen to my servers, it's not a big deal at all for this guy to say, OK, I was trying to forward something to the next guy in line, except he seems to have collapsed and keeled over. I will just skip over him and contact the fellow after him. And so this is the primary means by which the system gains its fault tolerance properties. So what did I end up showing to you? Well, I end up showing to you a system for locating the data in a way that preserves locality. And I ended up showing you a protocol that gives us atomicity, ordering, replication, and relocation all in one fell swoop. And it's fairly straightforward stuff. Like it's not some moon science, so to speak. So let's see. The next thing I want to very briefly discuss, and I'm not going to get into the details of the protocol for doing this, are multi-key transactions. So in many settings where NoSQL is deployed, what people want to do on occasion is they want to update multiple accounts or multiple objects at the same time and do so in an atomic fashion. And with first-generation NoSQL stores, doing this is essentially impossible. Why? Because there's one server that holds one object, there's another server that holds another object, and if we were to take the world's simplest example for this that database textbooks typically use, let's take a banking example. I want to make sure that I deduct $100 from Rob's account and put $100 into my account. I want those two transactions to happen either together or not at all. And I want to make sure that nobody else perceives a state of the system where half of the transaction has taken place. So how do I do this? Well, the easiest thing I could do is I just spray these operations onto my cluster, and I pray that nothing happens, that none of my servers die at the wrong time, or that nobody does a backup in the middle. Because if somebody does a backup in the middle, they will see an inconsistent version of my bank. They might actually see more money than there is in my vault. They might see less money than there is in my vault. So maybe one is less of a problem than the other, but either way, there's an inconsistency, and that shouldn't happen in a well-designed system. So if I want to protect against this, I could use, people would say, why don't you use a heavyweight algorithm like Paxos or two-phase commit? So those are fine, and in fact, there are many database systems that actually do this, but we have a much better way of achieving the same result. I'm not going to go into the full details, but I do want to give you the insight and intuition behind how it works. So this is a protocol called Warp, and it's an optimistic concurrent protocol for ensuring that transactions are atomic, that they have acid properties. And the way they work is actually fairly straightforward. So the key observation is that if somebody over here, two people here, A and B, want to do a transaction, that's great. Okay, so they can do that transaction without going through a broker, without going through a transaction manager, without having a heavyweight protocol that involves everyone or a subset of people. In fact, all they need to do is I just have to issue those transactions to those two nodes, as long as nobody else is interfering with them. So you can easily see that if A and B are transacting over here, and Y and Z are transacting over there, those are completely benign to operate in parallel without any overhead. I don't need to find a particular point in time and assign a particular order to those two sets of transactions because they're completely independent from each other. But there is a catch, right? The catch is this. If A is transacting with B, and B is transacting with C, and C is transacting back with A, then I have a problem, or I could have a problem. And that's the one scenario where we need to step in and make sure that these operations are well ordered. So what HyperDex Warp is essentially a very lightweight protocol for detecting these kinds of cyclical situations that can break transactional guarantees. So this protocol we call linear transactions. We have a paper that describes this in more depth, but I don't want to go into the details of it, but the core idea was this. That is, by making sure that I never have a circular set of dependencies that can break the timeline, that can break a coherent view of what happened in my system, then I can suddenly ensure that independent operations proceed without any overhead, and those that could conflict get sequenced properly. So our system is quite mature at this point. We have bindings for C, C++, Python, Go, Java, Ruby, and Node. It's open sourced under a BSD-like license. You can take it. It takes about 30 seconds to install and 30 seconds to actually deploy a cluster. You don't need to go to long, complicated lengths to set a HyperDex cluster up. We're very proud of how self-organizing it is. In fact, our background prior to this work was peer-to-peer self-organizing systems. That's where this work came out of. Let's see. I want to show you how this thing works. It's actually fairly straightforward. So the basic operations you might imagine, like putting an object, look like the following. So in this case, we're doing a put into a phone book of an object with a key here. And what you see over here is a bunch of operations. This is John Smith, etc. And when I do a get, I get the object that I put. This is very simple stuff. The one caveat or the one cool thing about this is I am guaranteed to always get the most recent version of this object. I don't need to worry about getting an out-of-date version. I don't need to perform reconciliation on this object. So I could also do searches that are incredibly efficient. So in this case, I could say, for example, find me every single object that has the first name John. And because of that hyperspace hashing trick that I showed you, I will be able to get all of the Johns listed under this search query. The system also has atomic operations. So in this case, this is a conditional put. So what we're doing here is swapping out John Smith's phone number. And the first time you do it, it says true. This operation succeeded. The second time you do it, it should return false because the phone number has already changed. So you actually have a very strong guarantee there. the atomic operations expand. We have a huge number of them. So this is just showing atomic add, where we add a single digit to a phone number. It doesn't really make sense. I tried to just sort of keep the schema the same. But the core idea here is we have a whole number of atomic multiply, divide, subtract, add, string prepend, string append, etc., that are individually atomic on a single key. In addition, we have asynchronous operations. I think we're one of the few NoSQL data stores that give you a way to bulk load a lot of data by giving you async operations, where the operation returns immediately, and your client and the server cluster in the background will push the system through. So in this case, you do something like async put, you get back a response, and you can have as many of these as you like, outstanding. And at some point, if you actually depend on this response to be completed, you can do an individual wait on that operation. You can wait for that particular async operation to finish. So if you have a lot of bulk data to load, this is the preferred way to get it into the system. So let's see. So there are other things that are kind of neat. So I talked about integers and strings until now, but the system is kind of like Redis in the richness of its API. So it supports lists, sets, maps, as well as documents. It also supports just regular old JSON documents. And you can see that you can mention something like tolerate 2 failures, and it ensures that every single write is actually written to 2 replicas. So ops like list rpush and so forth, they are all supported, all of the obvious things you might want to do with lists and maps and so forth. And in fact, atomic operations within lists, within maps are also supported. And finally, there's a very nice and very elegant interface for transactions. You essentially say, you acquire a client to a HyperDex server, and you say, look, I'd like to begin a transaction. And in that transaction context, you start issuing gets and puts, or other operations that I mentioned. And in this case, we're looking at EGS's account balance, we're looking at Rob's account balance, and we're taking out $1,000 from one and adding it to the other. And these operations are not going to be visible to anybody else until I do a commit. And when I do a commit, they will either succeed all at once in both places, or they will fail, they'll abort. There will never be an opportunity for somebody to observe a partial effect from an asset transaction. This is very much like the good old days of RDBMSs, except based on NoSQL principles. So one big worry you might have is, okay, this is fine and dandy, but you probably ended up taking a lot of shortcuts, or you ended up doing things, you ended up acquiring a lot of overhead to implement this. So I want to show you the results from an industry standard benchmark. This is the Yahoo Cloud Serving Benchmark, known in short as YCSB. And in this case, we're writing to 2 replicas of the data. And I want to show you the results for a MongoDB versus HyperDex comparison. So if you look over here, you will see that this is thousands of ops per second. And here is MongoDB set up in an academic setting with 16 servers. And this is HyperDex. And you can see that we're about a factor of 2 to 4 faster than Mongo, depending on the benchmark. So YCSB has different benchmarks, A through F. Each corresponding to a different mix of Yahoo sort of holdings, Yahoo services. And so behind the scenes, what you see, for example, this is the B benchmark, which consists of 95% read, 5% writes. This might be a very common operation in a big data setting, a very common mix of operations in a big data setting. You can see that the blue lines that represent HyperDex are a lot faster than the Mongo lines that are green. You see this staircase effect because of the sharding. And you also see that HyperDex achieves 100% of its latency under 100 milliseconds. So I'm going to skip this stuff. There is a cost, however. Right? There is one cost, which is, like, nothing comes for free in the distributed systems context, which is HyperDex's costs are correlated with chain length. And so this graph shows you chain length on the x-axis and operation latency on the y-axis. And indeed, as the chain length grows, the operation latencies might grow. And in our settings with customers who have deployed HyperDex, we typically see chain lengths somewhere around 10 to 12. But here we plot it all the way out to 22. And even then, these kinds of latencies are far below what you see with first-generation NoSQL data stores. And the system scales as you add more nodes. This is throughput in millions of ops per second. This is nodes, and as you throw more and more into the cluster, it will auto-integrate them, auto-scale, and give you a very nice improvement in throughput. So finally, I want to talk a little bit about the transaction situation. So here in this benchmark, we're showing HyperDex without transaction support. We're just issuing all the operations without encapsulating them in a transaction. So this is, in a sense, the best that we can do. It's also the best that I believe anyone can do. So this over here is the results of a two-phase commit protocol from regular databases. And the keynote thing to notice about two-phase commit protocols is that they end up involving more than the required number of servers in any kind of a transaction operation. Like in order to sequence transactions, they might end up placing unrelated transactions in a particular timeline. And that involves some overhead. And in fact, it typically involves so much overhead that they're about a factor of 3 slower than us. And if you look at warp, this gives you ACID guarantees. This is non-ACID HyperDex. This is HyperDex with warp. The overhead that we pay is only 4%. So I'll skip over this. So the performance summary is that we outperform other systems by a factor of 2 to 4 for gets and puts. And we outperform Sinfonia two-phase commit by a factor of 3 for transactions. And the overhead is essentially just 4% of a regular non-transactional NoSQL store. The latencies are predictable, and the resources, as you add more resources, the system scales well. And I want to sort of end up on a sort of a note of hope. So I want to sort of go back to the CAP theorem and try to put our work in context. So here is what happened with CAP. About 14 years ago, Eric Brewer came up and said, look, I have this theorem that of consistency, availability, and partition tolerance, you can achieve at most 2. So that's a very sexy, very catchy thing to say, and the developer community latched onto this. And what ended up happening is that the first generation NoSQL data store companies ended up sending their salesmen from door to door to door in Silicon Valley, where the salesmen come in and say something like, look, because of the CAP theorem, you can have at most 2 of consistency, availability, and partition tolerance. What they don't say is consistency is incredibly hard to get right. Okay? So they say, well, look, because of CAP, you can have at most 2 of C, A, and P. And so we're going to give you A and P. Okay? You have to give up on consistency. It's kind of like Lent, right? So you have to give something up just to atone for your sins. So I want to tell you a little bit about why the CAP theorem is not as meaningful as people thought and why you don't have to make that trade-off. The very first thing to notice is that the CAP theorem does not type check. So if you were to look at these terms, consistency, availability, and partition tolerance, they seem like they are equivalent or comparable. In reality, they're not. Consistency is a property of a system. It's, in fact, a safety property. Availability is a property of a system. It's, in fact, a liveness property. And, in fact, it's the mother of all liveness properties. You cannot have a liveness property stronger than A. Now, what is partition tolerance? It sounds like a property of a system, but what it's really doing, if it were a property of a system, it would be a liveness property. But they already have the mother of all liveness properties right here. So what it's really saying is, I have a tweak on my failure model. My failure model admits partitions. So already you can see that this 3-way trade-off is kind of confused. It's the result of muddled thinking. It is not a clear set of 3 adjectives that pertain to systems. So then what's behind this CAP theorem? What's the proof of this thing? What's the insight? Well, the insight is very simple, okay, and the proof is very simple. The theoreticians who ended up proving this simply say, look, if you have 2 hosts and there's a single link between them, and you want them to always give you the same answers to be consistent, and you want them to always be available, then you can't have that. Why? Because in a partition, the adversary comes in and disconnects the connection between these 2 servers. And so when you get a query on the left-hand side, you can't come up with the answer, the most recent answer, from the right-hand side. So if you try to be available and return responses, well, then you'll have to return out-of-date responses. Or if you don't return a response, then you will have to have given up on availability. So this is true, okay? But the problem here are that the CAP definitions are not what you want. This is not how you want your C and A to be. In particular, availability is defined as every host must respond to every query it receives. And that is not a sensible way to define things, because as distributed system designers, we typically think of availability at the system boundary, not at every server level. I do not care if my data center of 30 to 100 hosts, let's say, has a fault in it. Okay, that server is not required to answer responses when it's down. So that definition of A is incorrect, and that's what causes all the confusion. And further, the definition of the failure model is all too powerful. In essence, what it's saying is if you have an adversary who hates you, you've angered him somehow, and of course now you're going to be in a position where he can come in and take away your entire network. In the proof sketch that I did, my entire network was one link, and the adversary was allowed to actually come in and cut that link. So, of course, in that scenario, there's scant little anyone can do. And in fact, if we're going to be in this business, I can give you lots and lots of theorems that sound about as insightful as the CAP theorem. So I'll give you the not A theorem, for example. Availability is impossible against an all-powerful adversary. We know this. Right? If you anger God and he pulls down all of your servers, well, then your cluster is no longer available. Okay, is this an insightful theorem? No. This is a very dumb theorem. It's a tautology. The problem with the CAP theorem is not that it's wrong. It's that it's not even wrong. It's unfalsifiable. It's a simple tautology. You want two things that are in conflict with each other, and you can't have them when your adversary is all-powerful. So what of CAP then? So what did we do to get around it? Well, essentially what we're doing is we're saying, look, tell us the number of failures you want to tolerate, and we are going to guarantee you that you'll be able to tolerate those failures. Of course, if your failure boundary is undefined, that is, your adversary is all too powerful, then there is nothing I or anyone can do to protect against it. That, of course, I have to give it to the CAP theorem. But the moment you can define, this is the threshold that I'd like to be able to tolerate, these are the number of simultaneously down servers I would like to be able to deal with at any one time, then we can make forward progress. So is there a sort of why is the CAP theorem so popular then? Is there some kind of a deeper truth that it's getting at? And I think there is. And there is something called a CAP theorem. It's just not that CAP theorem that people talk about. The real three-way trade-off in a distributed data store is between consistency, availability, and performance. That is what it was getting at. And performance is the reason why people actually ditched RDBMSs for NoSQL. And so it's kind of interesting that the next generation NoSQL data stores like HyperDex are actually able to achieve both C and A, and do so while they're about a factor of 2 to 4 faster than the existing systems. And this is essentially due to those sort of slightly more advanced data placement and data relocation tricks that I showed you before. So the system does a couple of other things quite well. So one of them is backups. It's trivial to do backups in HyperDex. This is not your grandfather's backup system. You say, do a backup, and in less than a second, you get a consistent cluster-wide backup on all servers. And now it's going to take you some time to transfer them, but that transfer happens in the background. And what you are guaranteed is that if you had to restore from a backup, God forbid, but if it had to happen, you would get back to a well-known, well-defined state. And we also have security in the form of something very elegant from Google called Macaroons. So we can protect data items at the granularity of a single object. I can say things like, this object is only visible to Ruben, and only he and only somebody who possesses the key, the passwords that he does, can actually access it. So if my cluster is, if the front-end web servers are compromised for whatever reason, the attacker will not have access to the entire backend database. So finally, the system configures itself. It supports many versions of Linux and Mac OS X. It works well with Docker. It works well with a lot of settings where you need to just quickly bring something up. And we have a workshop tomorrow that Robert, my co-founder, is giving. So if you want to come by and see this in action, you can come by and see it in action. So I want to end, as I said, on a positive, happy note, that the kinds of systems that people thought were inconceivable, impossible because of the CAP theorem, turn out to be very, very, very doable. And we're not the only ones in this space. In fact, when we were the first one in this space, and we got back a lot of pushback until Google came along with Spanner and showed that if you were to make certain assumptions, similar in spirit to the kinds of things that we did, you could get around the CAP limitations. And so that was actually a big boon to us, because suddenly we're like, hey, we're not alone anymore. We were the first indeed, but now there are other systems that are able to provide strong guarantees and strong performance. So with that, I'll wrap up. Thank you.